Hi there, my name is Ukendar, and today I'll be doing a demo lesson on pressures within a fluid for students who are going from GCSE physics into AS and A-level physics. So we'll begin by introducing the equation that we're looking at. We'll then look at how we can derive this equation mathematically, and then we'll move on to some more practical applications of this, equation, and then, if the students are interested, we could do a challenge that's seen in the bottom right corner. So, to begin with, let's look at the equation. So, when we're looking at the equation for pressures within a fluid, we are examining three key variables on the right-hand side. We have the depth that the object is within the fluid, we have the density of that fluid, and we have the gravitational constant. So let's just make sure we know where these are coming from in relation to the diagram over here on the left. So, if I just zoom in quickly. So we have, let's say we have a ball in a fluid, and this fluid is water. We have to label the depth that we have the fluid, or that we have the object within the fluid with, and that is this dimension here. We have the density of the fluid, that's just the mass per unit volume within that fluid. And with that, we also have the gravitational field constant, which you'll know is about 9.81 meters per second squared. This is the rate that any object on the Earth's surface is going to accelerate towards the center. Now let's look at where each of these, quantities come from when we try and derive this. Now, as we have learned at GCSE, pressure is simply force per unit area. So we can go from this equation, force divided by area, to understand how we can derive this equation. So if we're in a fluid, we know that the only, force acting on the object itself is the weight of the fluid above. Now, how do we visualize this? Well, we have this column, and if this is a ball, we know that it's a cylinder because, well, if you look at a ball from the top down, it's a circle. So we have a column of fluid that has its weight, and this weight is pressing down on the ball. So we have the cylinder, and we know that the cylinder will have a density of rho, that funny P that we saw before. And we also know that it has these two values, the cross-sectional area of this cylinder and the height, which you'll recognize as being the same as from before over here. So, now that we have those two defined, we can look at the force of weight that this cylinder presses down on the ball with. So, again, if we look back towards the equation, this force is actually weight, and we know that weight is equal to mg. So we need to work out the mass of this cylinder. Mass is equal to density times volume. And we know that the volume here is simply the cross-sectional area multiplied by the height of the cylinder. So now that we've done this, we can simply insert this back into our equation for the force. So we have rho A H G. That is the force of weight pushing down on the ball. Now we need to understand how to get this into pressure. Again, if we're looking at the ball from the top down, the plan view, if you've studied tech, you'll know, we know that the cross-sectional area is the same as the cross-sectional area of the cylinder. So what we know is that the area over which the weight acts is the same as the area of pressure. So we know that pressure is now equal to the weight of the fluid, rho AHG, divided by, again, A, because they are the same. So now we know that P, if we cancel out the A's, gives us our target equation of H rho G. And that is that. Now, moving on to how we can actually use this equation. So we know that with pressure in a fluid, there are only going to be very specific scenarios where you need to use this. So if you're thinking about, like the lost city of Atlantis, for example, you'll find that the immense pressure or the immense weight of the water that's above the city is going to have an effect on the buildings. It's going to make them crumble. So we can use this equation to identify how much pressure is acting on the city. And once we've done that, we know that the force is simply pressure times area, as I've written here. And we know after that, we can use stress equations and fatigue equations that you'll learn later on in your physics career if you want to. And from there, we can identify roughly how long these buildings will last, how long they can last under the pressure, and what we need to do to reinforce these buildings if we were going to construct a new Atlantis. So yes, definitely very interesting, I guess, examples of where we can use these equations. Now, if the student is so interested, I know that I'm going a bit overboard here, but the student can now use the equation, and because they've developed an intuitive understanding, use it to understand exactly how to explain this experiment. So just to go through it briefly, the weight of the water above a certain point in this liquid is going to increase the deeper you go. So that means if you're at the bottom here, you will have a greater amount of water above you and therefore a greater pressure. Now this pressure will act out through these equally sized holes. So because it's the same area, we know that the force is going to be greatest at the bottom. And because the force is greatest at the bottom, the acceleration is greatest at the bottom due to the equation F equals ma. And because the exit mass of water is the same for each hole, the acceleration will be greatest here at the bottom. Therefore, it will accelerate the furthest horizontally before gravity eventually pulls it down to the ground. With that, I'll conclude this lesson. I hope this has been a bit more lively, a bit more engaging for whoever might be watching, and ultimately I hope to hear from you soon. Thank you.